Okay. So let's say we have calculate the integral of tangent. Okay. Now, the reason you haven't seen this before is because tangent doesn't show up as a derivative ever, does it? Tangent secant does, but tangent all by itself doesn't. So I don't know what you could substitute at this point that you could end up getting tangent, just tangent. And you're not going to invent anything. You know, when we had the one over here, we could mess with this. We had the rest, but if it didn't show up, we couldn't mess with it. All right, so let's try to substitute an identity. Remember what tangent x equals? Sine or cosine. Okay, and remember, they are derivatives of each other, right? Okay, so if we use one for u, the other one will show up in the du business, and so then we're good, okay? Now, here's the next question. What do we want to use for u? And again, this is, you can kind of think ahead, but sometimes, what do you want to try? Kate, I'm going to leave it up to you. Just sine. Okay. So, all right. So du equals what? It's just whatever.
Cosine.
Okay. So du equals cosine x dx. Okay. So will that work? Ito says no. Why not, Ito? Well, you got cosine on the right there in dx, but it'll be over cosine. Okay. Well, when we do this over here, cosine x times dx is not the same as this. That's dx divided by cosine x. We cannot create that. We can't pull it around because it's a variable. We can only pull constants around to the front. Okay, so that's not going to work. So what's our other option? Cosine. Okay, and you're going to figure this out when you have enough experience. But all right, so what's the derivative of cosine x? Negative sine. So du equals sine of x dx, which we have, right? I'm looking at it. And we can throw the 1 over to the other side. So we have this, right? So that's going to get replaced with what? Negative du? Okay, which is negative, what's left here? And I put du back. You mean 1 over u? Okay. We don't start substituting this cosine sign back until we've got the integration done. So what's the antiderivative of 1 over u? ln of the absolute value of u. All right. Okay, now we can put our u back in. Negative ln of, we used cosine of x plus c. Remember, cosine of x is not always positive, so if you didn't have the absolute value bars there, that would be different. And remember, you can't take the ln of a negative number, so that's why you got to do the absolute values. Okay, sometimes if it's ln 5, you can totally use them, leave them out. But now, if you think about the backwards and to take the derivative going back, you do ln of this, okay, times the derivative of that. So there would be, so you'd have it. But don't forget about remembering the derivative of this equals that. Okay, well, it would equal that. Okay, so this is using trig identities. That may be something that you can do if you don't know how to find the integral of it. Okay? So that's one trick. Anybody have a question on that slide? All right. This one looks like it's normal, but there's a little twist in here too. Okay, what do you think about u? 2 plus x, okay. So the u equals 1. That's right. Okay, but we can fix it. All right. Wait. Okay, this is u, right? We have dx and du just basically swap out. Okay, but x squared is a problem. But it's really not. Because what is x?
U plus 2. U minus
Oh, u minus 2. So we can put that in here. Everything's in u, we're good. Okay. Now that still looks like a pretty complex integration, but okay. So watch for that where you can manipulate and kind of substitute back in. Now, how am I going to integrate that? It looks pretty complex. I don't want to have to use another. Can you simplify that at all? Combine what, Angela? Yes. So this squared is what? U squared minus 4u plus 4. Is that what you were thinking? Okay. Yeah, she says. She sounds like my granddaughter. She says, yeah. Okay.
That definitely looks simpler.
It's definitely simpler because it's got everything in terms of powers, and you can do powers. Okay. All right. Ready for the antiderivative, Madeline. Yeah. Wait. What's in front?
I said 5 halves.
Yeah, I was hoping you'd change that answer.
2/5.
7. Remember, you're dividing by that.
Oh, sorry.
That's okay. So dividing by 7 halves means multiplying by 2 sevenths, right? All right, take over from that. Okay, you were kind of mixing up derivatives. All right, read, do the next one. And you don't have to simplify, just do it like you would do it on your paper. So you already divided it. You're dividing by 5 halves. The 4 staying here. Instead of dividing by 5 halves, we're multiplying by 2/5. Okay. So that's her 8. Where she got that. All right. Angela, do the last one. Over what? 3 halves, which is really multiplying by, is that what you said, 8/3?
Yes.
All right. Plus, see, right? All right, put our u back in and we're good here. U, remember, what's 2 plus x? So 2 plus x to the 7 halves minus 8/5. 2 plus x to the 5 halves plus 8/3. 2 plus x to the 3 halves plus c. Okay. That's a lot of shift here. Okay. So watch for some manipulation. Just don't. There's got to be something you can do because there's not going to be integration that I'm going to give you that you don't know how to do. you know, if you go on the internet and do integral problems, there's going to be plenty that you are not going to be able to do in Calc 1. But certainly not in class, certainly not in your book. I'm not going to sign any. We're almost done with Chapter 5. We're going to do one more thing. So this is as big as it gets. Okay? So we got trig identities that we can do. We've got some goofy manipulation. Let's move on to definite integrals. It's the same idea up to a point. This is your regular, of course now we have numbers here for definite integrals. Okay, what we do is we change, and the thing is we don't have to go back to the x's, we treat it with the u's now. So let's do one and I'll show you what I mean. Okay, so we're going to do the integration just like we would if the numbers weren't here. Okay, so we're going to think, all right, I certainly don't want to multiply x cubed plus 1 times itself 10 times like we did that squared problem, and then we threw the x squared through. Does anybody want to do that? I don't know. Okay, no, just say no. All right, so that means we got to substitute. All right, so what do you think about you, Charlotte? What do you think it should be? Yes, and if you're thinking ahead, you're going to get 3x squared-ish, and you got the x squared sitting there, so that's good news. Okay, so that should work. That is 3x squared. Oops. I don't have the 3, so I'll get rid of that. So what's that? 1/3 du. Okay, so here I go. This is u to the 10th. This becomes 1/3 du. Okay. Now here's what's. Okay, these limits right here were in terms of x. We don't have x anymore. We don't want to go back to x because that's just going to complicate. So what we're going to do is we're going to say, all right, let's find the u of 1 and the u of 2 and change our limits to accommodate u. So here's u. What's the u of 1? Right, that means plug in. 1 cubed plus 1 is 2. What's the u of, what's the other limit? 2. 2 cubed plus 1 is 9. So our new limits are 2 and 9. Okay? Now, we are not going back to x because we switched everything. We switched our thing to accommodate u. We switched our limits to accommodate u. We're good. We don't have to go back to x ever. Okay? So, 1/3. What's my, and this is going to hang out just like it always does. What's my antiderivative of u to the 10th, Miss Megan? No. U to the 10th over 10. Okay? Sorry. Yes. Correcting you wrong. All right. Over 11, right? Okay. Now, remember definite integrals. Do we have to see? Nope. Okay. But we do have to do some subtraction, remember? Okay. So 1/3, we're going to multiply, whoa, I guess we might as well do 1/33, huh? Okay, so what's that, 9 to the 11? Yikes. Minus 2 to the 11. We're done with it. We're not going any further than that. Okay? So, let's get your calculator out. And let's just plug in from the very beginning. Okay? If you have a integral from the very beginning and you have your calculator, you're not going to do any substitution. You're just going to plug it in. Math 9. 1, 2, x squared, parentheses, x to the third plus 1, end of parentheses, to the 10th. X. Okay. Whoa. That's a huge number. Okay. Now that's probably a rounded number, but let's now put the new improved one. So let's do 1/3, then math 9. I'm doing the U one. 2 upper limit 9. Okay, now the calculator only accepts x's, so we'll just, doesn't matter what our variable is, x to the 10th. With respect to x, we should get the same answer. Okay? If you want to really make sure you have it, 1/33, 9 to the 11th, oops, I forgot my parentheses, minus 2 to the 11th. In there. There it is again. Okay. So there you have substitution, definite integrals. But that's going to be a problem because a lot of people want to go back to x. You're going to complicate it because you're going to have to put in, you can do that, but then you're going to do, 1 cubed plus 1 here to the 11th. Okay, you don't want to have to put x back in. You don't have to. And you do on the indefinite ones because your integral needs the same variable. Your antiderivative needs the same variable as your. Okay, any questions on that one? Just your new little machine yet there, Miss Jessica? Pretty cool, huh? Yeah, brand spanking new one.
So small.
Yeah, they make it spinnier now. Yeah.
Everything.
Yes. Okay. So you want to try this one by yourself? I'm going to shut this off. Should be good. All right. Here we go. Now that is not a. So don't assume now just because we have substitution, everything is going to be substitution, ladies. Okay. So you got a U planned here. You're going to do ln of x because the derivative is, and we have that. So it seems like you're going to find it. Okay. And don't be afraid to try something and, oh, that doesn't work, I'm going to try something else. So, you're not always going to know what it is off the top of your head. And even when you think you know what it is, you're like, no. Okay? All right, so 1 over x, we have it right there. Okay, so here we go. U of 1, U of e. Do not even put the 1 and the e up there because otherwise you're going to forget to change your limits. Okay? So ln x is now u, and 1 over x dx is du. That's easy, isn't it? All right, so what's my antiderivative? Okay. From, I didn't do u of 1 here. U of 1 is ln of 1, which is 0. So that's 0. U of e, which is ln of e, equals 1. Or 1, 0, and 1. So what do we got? And you can pull your 1/2, or you can drag it with you. It doesn't matter. So what do we got? 1 minus 0. The answer is, okay, there's your answer. That looks a lot worse than it was, right? Okay. All right, you wanna try that one? Okay, so when you're looking for this, to see if this symmetry works, you have to note, first of all, that we have opposites, okay? If we don't often have opposites, then don't even bother because it's not going to be a factor. So if it's like 2 and 4, like it doesn't matter if it's odd or even because it's not going to help us any. And this is -4. I don't know why those negatives are kind of losing it right here. Okay, so then we see this, then we say, all right, if it's odd, it'll save us a lot of work. Let's check it out. So how do we check if it's odd or even again? Plug in. Okay. -x minus, what's -x to the 5th? Okay, so that'll make that x to the 5th, right? And what's cosine of -x is the same as cosine of x. Good job. Okay. Is that the opposite of?
No. Wait. Oh, because yes.
That's f of -x, which is -f of x, is it not? Okay, so it's not. So tell me what this integration equals.
0.
Okay. Now it would be quite the feat to integrate that right at this moment. I don't think you can do it. Okay. So just know if you don't know how to do it, and you got opposites, just look. Okay, so clearly this one is not an odd function. I can go by looking at it. Can you? Because you got an x to the 8th. But if you, again, you see opposites, you say, oh wait, that's -x to the 8th over 2. This is f of -x. I'm just looking because I noticed this situation. That's still x to the 8th over 2, which is the same as f of x, which means it's even. Okay, this isn't that helpful, but here's how it works. Okay, if it's even, I have really 2 of the same thing. It's that symmetry that I'm using. And I'll show you the graph here in a minute. All right, so that means I can change this to 2 of 0 to 4. Okay, x to the 8th over 2 dx. Okay, I'll show you the graph in a minute and pull that together. This 2 can come out. 2 over 2 is 1. Okay, antiderivative. X to the 9th over 9, no substitution involved, right? 4 to the 9th minus, all right, there's your answer, whatever that is, okay? All right, now let's take a look at the graph and you'll see why that makes sense, hopefully. I want to graph, sorry, widths. X to the 8th over 2. X to the 8th over 2. I want to make sure I'm just included between -4 and 4. It's okay. It'll still work. It'll give us, yeah. Okay. So that's symmetrical. All right. Which means I have the same thing right here, actually, the same thing, 1, 2, 3, 4, let's say 4 is right here. All this is under the curve, right? So -4, it's the same stuff. So that's why we're like, we'll just talk about this and do 2 times 2. So that's the general idea. Does that make sense? Okay. Honestly, the integration when it's even is not that good, but the odd is fabulous. Like you don't even want to miss that. Fabulous, that memo. Okay. It's nice because you don't have that negative, minus and negative business, because one of them is going to be negative if that occurrence is going to happen. So, all right. I think I'm done finally. All right.